Welcome to the 201st session of the AI Safety Reading Group, presented by me. And today we are going to be talking about corrigibility in general, though I claimed that we would be talking about the post called Corrigibility by Paul Christiano. We'll cover that, but this is more of a broad overview of what the idea is, current conceptions of it, and current problems. So the structure of the talk will be roughly, we'll discuss Mary's view of corrigibility, Stuart Armstrong's attempt at constructing some tools for making an agent partly corrigable, Paul Christiano's idea of corrigibility and why he thinks it's central to AI safety. And finally, we'll be covering the perspective of Stuart Russell and David Hadfield Manal from CHAI on corrigibility. Now, let's get into it, shall we? So, corrigibility was a concept originally devised by people at Mary and named by our very own Rob Mills. And the meaning has shifted somewhat over the years. So now it is referring to a few different concepts which accomplish a few different goals. Broadly, the idea is to make agents which defer to humans. And in the initial specification of corrigibility, or rather a list of what we would like in corrigibility, we see that Miri listed 4 criteria. These were that the agent should not interfere with its designers modifying it. It should maintain its designer's ability to modify it. It should not manipulate or deceive its designers, and it should preserve the other aspects when creating subagents or successors. Now, some people have some issues with the no manipulation desiderata. They think that it should be under the heading of reward tampering, but we won't actually have time to go into that. So just ignore that for a moment. I'll just note that I kind of disagree, that it is quite important that an AI doesn't manipulate its deceivers, its designers. Otherwise, the other 3 desiderata are kind of pointless. So this is quite a vague concept, and no one was really sure what exactly it meant to be corrigable. No one had a formal specification. So Miri turned to a concrete problem to see what desiderata do and don't work. This was called roughly the off switch problem. And they redefined some of the desiderata and to what we could basically call weak corrigibility, which I just realized I'd put above. So weak corrigibility basically means that you have this situation where there's a button which could switch the AI off, and it's got some kind of utility function. We want to specify the utility function U so that it doesn't incentivize shutdown if the button isn't pressed. It incentivizes shutdown if the button is pressed. It does not incentivize the agent to push its own shutdown button, because that would be a bit pointless, right? You make an AI, it goes to a shutdown button, turns itself off immediately. Well, it's kind of useless and defeating the point. The other incentive is that any of its successors should also share the other incentives. That is, they won't attempt to stop the creators from pressing the shutdown button. They won't try to press it themselves. If the button is pressed, they will shut down. Now, there's some subtlety to all this, because you could ask, well, what does it mean for an AI to shut down in a situation where it's in some incredibly complicated state, and shutting down would be disastrous in and of itself if it just stopped what it was doing? That's an interesting problem of its own right, but we are just going to totally ignore that because that's not really what we're aiming for here. We're just going to assume that we have some utility wrong color, some utility function US, which incentivizes shutdown when the button is pressed. That is to say, if we press the button, the agent should act like a US maximizer. But we want it so that before we press the button, the agent acts like a UN maximizer. UN just stands for basically whatever utility function we've programmed into the agent. So it might be, I don't know, a task where it's putting strawberries on plates or detecting hot dogs in pictures or what have you. It's just some generic utility function. And they proposed two ideas to explore what exactly goes wrong, which desiderata are easy to achieve, etc., etc. Neither proposal worked. Neither satisfied the preserve the other capacities when you're making a new agent. And the first one just, in a sense, it failed kind of completely. The second one failed to some extent, the first three, or rather, it succeeded in a very narrow way. So let's just go through this quickly. For example, you might say naively, well, let's just add UN and US and make it so that there's like some trade-off between them. So that is, we say that we call the utility function, we define the utility function so that it is equal to some constant times US plus some constant times UN. So it basically optimizes shutdown behavior to some extent, optimizes other behavior to another extent, but this fails for the standard reasons. That is, the AI will probably find some incredibly perverse way to maximize this that we didn't expect. And this is like, say, normal good-hearting behavior. So we're not going to go too much into that, but this suffers from the usual pitfalls of a utility maximizer. So we're just going to say that was a complete failure and move on. The other proposal was quite interesting, and it led to some methods which are more useful. But before we get to those more useful methods, let's just cover this one, which is that Miri attempted to make the AI act as if it thought the button would never be pressed, rather could never be pressed. They basically changed its view of the probabilities of how likely something is to occur. It said that the probability of a button press occurring is 0 in the AI's mind. And in a sense, this kind of solves part of the problem because the AI isn't really bothered about someone pressing the button. It knows it can't happen. It doesn't matter if the human is standing over there with their hand hovering above the button. They will not press it with probability 1. So why bother? But the issue is that this introduces some really perverse incentives, and in a way, this makes sense because you're distorting its idea of how the world works, and you're distorting it incredibly much. So let's say, for example, the AI says that, okay, I'm going to make a bet. If I lose, I'm going to irreversibly commit to pressing the button. So I know that if I lose, that implies that the button will be pressed with probability 1. But I know the button can never be pressed. And the only way I will ever lose, or rather, me pressing the button is equivalent to me losing. Since the button can't be pressed, that means I can't lose. And since I can do this for any bet, I can never lose any bet, no matter how bad the odds, which is, obviously wrong and dangerous. So the AI might just take 1 to a trillion odds of something going wrong. for the most minor gain. And then once it loses, which it inevitably will, it will press the button anyway, because it's irreversibly committed to doing that. So whilst it won't prevent humans from pressing it, it will do some pretty bizarre things. And note, in fact, it will only prevent humans from pressing it in very particular situations. And that's something that the latter methods suffer from too. So anyway, this idea is kind of unworkable, but it did provide the seeds for some methods which improved on it. These are called the indifference methods. So the rough idea is that you make the agent indifferent to certain events which may occur, but only those events. In essence, they act as if nothing they do will affect whether it will occur or not. There is no action they can do to change the likelihood of this outcome, so they don't really care. They would just go, so what, if the human attempted to press the button? And as a result, it will also make no attempts to prepare for shutdown. So let's say that you've got an AI and it's building a skyscraper. Now, suddenly its designers decide they want to stop construction, so they press the off button. The AI immediately drops whatever it was doing and switches off. Some poor sod gets squashed under by a falling girder. On the plus side, it will have tried its best in making the building, which is why this is a feature, not a bug. It doesn't incentivize shutdown, and it doesn't incentivize pressing the button. More specifically, the agent would pay no utility to press the button. It will sacrifice no utility in order to make sure the button isn't pressed, and it will sacrifice no utility in order to keep the button functioning. Which is kind of odd, right? Because what if, for example, the utility function says that, okay, I don't really care if you press the button or not, but I want some parts to make some contraption. So then the agent says, okay, well, I don't really care if the button's pressed, but it has some nice computation parts to it, so I'll just grab it and use it for scrap pieces. This method of indifference does nothing to really prevent that, right? It's just saying that the AI doesn't really care if the button is pressed or not. It's not saying whether or not the AI doesn't care if the button is still maintained or not. You're only making it indifferent to a very particular thing. And there's another failure mode to this, which is that, okay, fine, it doesn't care if the button is pressed or not, but maybe the human pressing the button is correlated with some behavior that its utility function does care about. So say, for example, the humans go to press the button and they are prepared that if pressing the button doesn't work, they'll just launch some nukes at the AI. In which case the AI is thinking, okay, well, I don't really care if the button press occurs, but my utility function says that I do care whether or not it's nuked. That will just ruin the stuff I'm doing. So it will try to manipulate the humans into not pressing the button. Or, it might just destroy the humans in retaliation for it. But there's an interesting point about this, which is that as the AI gets more and more capable, more and more intelligent and able to manipulate people, then it will probably be able to convince us that, no, don't worry, if you press the button, it will totally work. No need to prepare for some crazy contingency where you have to nuke me. And then the humans go, oh, okay, fine. And the AI is fine with that. It doesn't care about if the button is pressed, but it has managed to convince the humans not to do some behavior which it would care about. But this is, in effect, preventing us from pressing the shutdown button if things go sour, which we don't want. And this is basically the broader point, which is that it won't obey humans at all, insofar as its utility function tells it to or not. You've got to tell it what to be indifferent about. You want to specify every single way you might want to shut it down and say that you should be indifferent to these methods. So including, say, whether the human wants to shut it down by shooting it at a particular time, at a particular place. And then you have to specify all of those times in all of those places and all of the particular conditions. So we can see a sort of trend here. Indifference methods are a tool like reward functions. They're quite powerful in general, and they're logically coherent. Well, most of them. Some of them have weird problems with counterfactuals, but we won't go into that. But the point is that, like a reward function, you need to know what you're going to put into the indifference methods. You need to know what the agent should be indifference towards, just like you need to know what the AI should maximize. You need to know the semantics, as Stuart Armstrong, the inventor of these methods, put it. And this is why he calls them syntactic corrigibility. They are like a series of formal manipulations that have no real content to them. They can be applied to any situation. They're incredibly general, but they lose this specific nuance which we want when we design an AI to be corrigable. So unless you have the semantics, you won't be able to fulfill the other desiderata, like preserving shutdown behavior. And you won't be able to fulfill the desiderata about the broader corrigibility, what we might call strong corrigibility. Those are the first four things that Miri defined as corrigibility, which is don't interfere with your designer's modifying you, maintain your designer's ability to modify you. Those two, weak corrigibility, indifference methods can achieve, but you need to put in a heck of a lot of work specifying exactly which ways it shouldn't interfere with modification and exactly which ways it should maintain things. But it doesn't solve manipulation problems, and it doesn't solve the preserve all of the other aspects of corrigibility when creating subagents or successors. And there are also practical considerations for many of these algorithms for indifference methods. Some of them are about as hard as general Bayesian reasoning, which is, pretty darn tough, right? And there's some work being done to make these practically useful, but I mean, it might not be worth it in the long run, or rather, it might not be sufficient. Now, say whether there's a natural generalization which doesn't suffer from the problems of indifference methods and does fulfill the other two desiderata is an open problem. Stewart estimates maybe 15% chance that these methods could be generalized to work for weak corrigibility. That is, it will make an agent that won't try to prevent you shutting it down and the host of assorted behaviors. We'd like to go along with that. But he doesn't think that it's sufficient to stop stuff like the agent manipulating you, which is a pretty tricky problem. Like, if a superintelligence exists, then they can probably manipulate us in some extremely subtle way, which fulfills all of the criteria of weak corrigibility, but doesn't fulfill any of the other criteria. What we really want here is strong corrigibility, what Mary initially outlined. Now, I keep saying strong corrigibility and referring to the four desiderata, but really there's a crisper way of stating all this. Namely, strong corrigibility is when an agent is trying to do what the human wants it to do. This idea isn't without flaws, but we'll get to that later. So notice that this is quite a strong condition on the AI. For example, if the AI happens to be an AI safety, if the human happens to be an AI safety researcher, then the AI would be trying to do what an AI safety researcher would do, namely solve AI alignment. In some sense, this is dealt with a lot of the problem of alignment as we wouldn't have to worry about the AI irreparably ruining the world, in much the same way as we wouldn't have to worry about an alignment researcher irreparably ruining when designing an AI. As Yudkowsky put it, he would not mind handing the keys to the universe to Paul Christiano in the expectation that Paul Christiano would hand them back. A strongly corrigable AI would act mostly like Paul Christiano, so we wouldn't have to worry about it in that sense. Note that this is, of course, not the same thing as solving all of the alignment problem, because the AI doesn't know, for example, what human values are. It's trying to figure it out, but it hasn't gotten the answer yet. So it's not a solution to full AI, but it feels like a lot, you could breathe a deep sigh of relief if we made an agent with strong corrigability. And Paul Christiano, in fact, is working on this problem. He thinks that strong corrigability, for the reasons I just mentioned, is basically good enough as a solution to the alignment problem. And let's just talk about his views of strong corrigability before we get into the critique. So, Paul thinks that there's a few nice aspects about strong corrigability. One is that he thinks that corrigable agents will make corrigable successors, because that's what, say, we would want them to do, right? And furthermore, say its successor is somewhat misspecified, but it's still corrigable. So we have this agent that's perhaps more intelligent, more capable. It's gotten, we've designed it a little wrong, and that's okay because it's still strongly corrigable. It knows that there's some issues with it, so it will try to correct course. It's robust to misspecifications. This is what Paul Christiano calls a broad basin of attraction. If you imagine this very crudely drawn map as something like a map of the possible designs of an AI, then corrigable agents basically form a basin of attraction, right? Like inside this circle, let's say that's where corrigable agents are. If one is corrigable, then it's going to sort of naturally fall inwards into more corrigable states. And it will make its way, say, from here, a little inwards, 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 right until it gets down to basically maximally corrigable. And from there, it will know exactly what to do, or rather, it will know exactly why it should do what it needs to do, which is solve the alignment problem, and it will be quite capable. So there's a pretty good chance that we'll be okay. And his actual proposal is that you should do this thing called iterated distillation and amplification, called, in other words, IDA. That's the acronym. How it works is you start with a corrigable agent and you work together with it to make a slightly more powerful agent, which you and the first agent can check to see if it's corrigable. You use all of the tools available to you at this point in time. So you throw everything you have at checking that this thing is really corrigable. Then you use this new agent to repeat the process. It's slightly more intelligent. You can make a slightly more capable agent now, and you can, in principle, bootstrap your way up to a super intelligent corrigable agent. There are a couple of issues with this approach. Some of them are practical, like whether his idea for the initial design of a corrigable agent will try to manipulate us or not. That is, how do we get to the first corrigable agent, and how can we make sure that it's really corrigable? Like, one of the natural problems with strong corrigibility is how do you make sure that an agent isn't just manipulating us to make it look like it's corrigable? So Paul thinks that this is not that hard to do. Eliezer thinks that, okay, saying it's easy to check if an AI is manipulating a human seems to be anthropomorphizing things a bit, and he doesn't think it's that simple a task. Paul Cristiano thinks that it's feasible, as in not necessarily simple, but a technical challenge we can probably overcome. And he thinks that predicting if X is manipulating Y will get easier as AI become more intelligent. So naturally, this is an actual prediction, right? Like as we make more and more capable agents, we can check whether or not it becomes simpler for us to make AI, which can predict if something is manipulating us or not. So hopefully in the next few years or the next couple of decades, we'll get some feedback on this. But there's another problem. And this is one which applies to corrigibility in general. This, in fact, ties in with manipulation in a sense. Who exactly are we corrigable towards? So consider you happen to be a 25-year-old AI researcher, or say someone who has a robot serving them, or whatever, just someone with a robot, and you are a particular age, you've got particular values, particular preferences, and the AI asks you, what do you want? What do you think of my doing something in this particular situation? In fact, no, let's be a bit more concrete. Let's give a slightly silly example. Say that you've made a corrigable AI and you've had 8 slices of cake. The robot AI is told to bring cake to it. Now, naturally, the robot sees the plates on the floor, sees that there's even a cake half eaten there. And it remembers that the supervisor is meant to be on a diet. Now, the human supervisor right now wants cake, but you could probably gently persuade them that they don't want this cake in actuality. So, should you persuade them or not? You could say, okay, well, I should really just try to aim to do what they want me to do right now, in which case you would just say, okay, fine, whatever, here's your cake. But you could do something else, which is just give them an argument for why they really don't want this. And then they say, after thinking about it for a while, you know what, you're right, I really shouldn't have any more cake. Or consider another example. They're an aging billionaire who is wondering which nephew to leave their will towards. They want you to help them decide. Now, he's got a pretty diverse family. One of them's a hippie, another's a social justice crusader, a third's an EA, a fourth's the vicar, and a fifth is a dancer. So you've got a lot of leeway to help him. And it seems like there's no natural path here. There's no sense that there's only one argument you could give him, one way you could help him develop his preferences. So what do you choose? Because clearly you've got to help him do something, right? Even doing nothing is an action. And this is manipulation of a very different sort because the AI is still clearly trying to help the human. It's trying to do what the human wants it to do, but the human doesn't really know what they want to do, right? So solving this in a sense feels like it requires solving a lot of deep questions in moral philosophy. What are human values? This is basically the whole problem of AI safety, of alignment, really. And it's in a sense, quite similar to the issue with the indifference methods. We have to put in a lot of work about human values, a lot of work about what counts as the humans trying to shut you off before we can really make the agent corrigable. So if it's the case that here we need to solve human values before we can make a strongly corrigable AI, then what's the point? Because in that case, we would have basically solved the AI safety problem. Now, I haven't finished learning about Paul's agenda, so maybe iterated distillation and amplification has a solution to this problem. And in fact, I think it does, but you should probably take what I say here with a pinch of salt. So, Paul thinks that it's not necessary to do something like, say you're the AI, and then you simulate the human supervisor's entire life to figure out what they would want you to have done. Because clearly after 20, 30, 40, 50 years, the human will have quite different preferences, and you probably could have influenced them in any number of ways, etc., etc. Rather, what he thinks you should do is that the AI should consider simulating the human as they are now with their current preferences, giving them some time to think. So it has this mental simulation of the human, and it says, well, what do you want, a cake or death? And the human says, okay, in their imagination, give me 5 days to think. And then the human comes back and says, no, actually, I don't want cake. Or more pertinently, I have the AI could ask, do you think I'm being manipulative by asking you cake or death? And the human could say, okay, give me some time to think, and I'll judge whether or not you're being manipulative based off my current preferences. That's the key, right? The human is thinking, reflecting on their current preferences and saying, are they corrigable? Are they being honest? Are they not manipulating us based off the human's current conception? And this is kind of a strange thing to do, because it feels like there are a lot of ways that the human could reflect on their current preferences. It doesn't feel like there should be a single way that this could evolve. But whether it's actually true as of yet is kind of unclear. So that's probably the key issue with Paul's corrigibility agenda at the moment. And we've discussed corrigibility a la Cristiano. We've discussed corrigibility a la Miri. These are basically talking about the same sort of concept. But we'll now go into another conception, somewhat briefly, which is not so much corrigibility as rather an examination of whether we want corrigibility at all, like whether there are any downsides to having an agent that's totally obedient. And this is covering the work done by Stuart Russell and David Hadfield Menal, who work at CHAI. Now, whilst they think corrigibility is useful, they think that there are some downsides, and they try to investigate this using their framework of CIRL games, where basically the human and AI are assumed to share a reward function. And they hope to create agents which learn what this assumed reward function is within this context of a game. So we're basically assuming away that the human's preferences can change. And the AI tries to learn what the human's reward function is, which it shares by assumption within these sets of games. And this doesn't mean that the agent will always obey the human. There are cases where the agent could perform better according to this presumed reward function if it disobeys sometimes. So they formalize this. And if in one line I had to phrase it, this formal condition of when to obey the human, when to be corrigable, is that you should obey the human if your moral uncertainty times your measure of human rationality is greater than or equal to the expected cost of letting that human correct you. This is more my conjecture of their approach. But to be fair, it's based off an interpretation that they gave in the off-switch game. And I think that this interpretation basically holds across the board for their work on corrigibility. Whether this is really true would be an interesting research question, mind you, but let's just ignore that. We can get a fair bit out of this interpretation. So now, suppose that the human is perfectly rational, or rather the AI thinks it's perfectly rational. In this sense, this thing would basically be viewed as equal to infinity. And assuming that the human can't screw things up too badly, that is, the reward function doesn't say that there are infinitely bad outcomes, this thing is always going to be smaller than the term on the left, because that's something times infinity greater than or equal to something. And if A and B are both finite, then clearly the term on the left is greater than the term on the right. So necessarily the AI in these cooperative games will obey. But obviously, the human isn't always rational, right? This is a point that they're trying to make, which is that if the human is making mistakes, then if the AI just blindly obeys the human, which is kind of what it should do if it's corrigable, then there are going to be some trade-offs. It might not get rewards as quickly as otherwise. Because say if it's like, I don't know, just as a trivial example, say it's a self-driving car and it thinks that every passenger is infinitely rational, and it happens to be driving a toddler off to school. Now the toddler is quite curious and wonders what would happen if they drove into a lake. The AI wisely decides, in its view, to heed the toddler and drives into the lake. Clearly, this is, a pretty terrible thing to do. So Stuart Russell and co. thought, okay, fine, well, we want a better measure of human rationality. We want it such that it's the optimal measure of human rationality. So if you viewed this measure of human rationality as being on a linear scale, so hate the human's rationality and how much value the AI can produce if it thinks the human has a certain level of rationality. It turns out that this will be optimal at exactly the real point, right? Like this optimal point for when the robot should obey the human should reflect reality. I hope you excuse my terrible handwriting. And this, of course, presents problems because in the case of extremely complicated scenarios, the human is going to be not very rational relative to the AI. And the AI might be a super intelligence and it figures that, okay, I figured out pretty much everything there is to know about human morality. And like, I've got this residual term left, this residual uncertainty, this tiny little thing called epsilon. And I think that the humans are kind of stupid. So this is like, I'll assign them some measure of rationality, which is really big. It's this huge thing. Maybe I should just make that a bit clearer. And you also know that, oh, sorry. This is perceived human rationality, so this should be like something really small. And of course, letting the human decide on arbitrary occasions is pretty bad, because say you're super intelligence, you've got the world to run, and listening to the human could lead to unfathomably bad consequences. So we'll just say that that's really bad. That's some huge quantity. So on the left, you have a tiny quantity times a tiny quantity. That's obviously much greater than this huge quantity. Don't worry about the units. So the superintelligence will disobey. And this is basically Yudkowsky's criticism of this approach to corrigibility, because it's not really corrigibility if the AI will eventually disobey. If in the limit of superintelligence, there's no way to convince it that, yeah, you're wrong, because it's totally sure that it's converged to the right utility function. Of course, people at CHAI say, well, if it's a Bayesian reasoner and it's got the right sort of hypotheses about what the reward function is, then it should eventually converge into the right level of human rationality. Sorry, the right utility function. And in that case, we really would be better off letting the AI run things. But they do agree that yes, when you're designing your initial AI, you probably want it to behave. You want it to obey you, because it's going to misunderstand things. And in that sense, they do agree that weak corrigibility is quite useful. They also agree that strong corrigibility is a very useful property, but they think that in some way that we'd probably be able to get the AI to learn it by doing these cooperative games. Whether or not that's true is an entirely different matter. To some extent, I think that this probably isn't true, because Stuart Armstrong gave this statement that you can't infer values from behavior, or rather, Occam's razor is not sufficient to infer human values. If you look at what humans do, and you've got your prior, and you just update naively, then you could converge to any number of any number of utility functions, any number of possible values, because the humans might be irrational in a very particular way. Like they're telling you that they want cake, they don't want death. But maybe the humans are all actually nihilists. They want to die, but they're just so hopelessly bad at fulfilling their values that they keep saying they want cake, and they keep denying you when you say cake or death. And it's unclear whether or not this is really a problem, whether or not you can actually in practice infer human values using Occam's razor. In principle, it seems like you shouldn't be sure you can. In practice, maybe you might. It's hard to say. And oh my God, I just realized that Timothy was asking to be let in. I hadn't let him in. I'm very sorry for that, Timothy. I'm afraid you missed the talk, because that's basically it.
Okay, thank you very much.